There we go. The final exam, which is really just the last midterm, it doesn't cover anything besides the last material on simple harmonic motion, waves, and sound. It opens Friday at 8 in the morning when the testing center opens, but the testing center is not going to be where it normally is. Because of the number of final exams that are given during that period, they're spread all over campus. And our class has been assigned to Richards Hall, down off the hill in room 144. And that will be open the entire finals week. Homework solutions are at max. The 2 exam solutions, the exams and their solutions are at max. Yes.
So no mock cones?
Oh, no, mock cones will be on there and beats will be on there. That's, yes. That, if you look at that exam preparation sheet that I gave you, right at the bottom, it has a special little note that says mock cones and beats will be on the exam. Okay, yes. There will not be one of those this time. Yeah, that was causing just too much stress. One of you, and I'm not going to name names because I don't know the name, was so set on knowing the right answers to the online exam that they created like 150 personalities, and each personality went into the test and took one question with A, and then they went in with another personality and took the same question with B to see which one got it right. I'm sorry. That's too much stress. Okay. The help section with me answering questions will take place tomorrow night at 7 in this room, and I will record that like always and post it to YouTube. Let me say something about these cookies. These cookies are Lebkuchen, translated cookies of life. And they're made only in one place, Nuremberg, Germany. And the factory that makes these cookies was just blocks away from one of my apartments on my mission many, many, many years ago. And that factory had a little discount store where they would sell broken cookies by the bag. And my companion and I would go every week on our P-Day to get a bag of broken Lebkuchen cookies because we discovered something very important. One of the most important things I've ever learned, and that is that broken Lebkuchen taste just as good as Lebkuchen that are not broken. Okay? Now that's important because some of us, most of us, all of us are broken. We're all broken cookies. We all are broken cookies. There was only one cookie that wasn't broken. But to our Heavenly Father, broken cookies are just as delicious as the unbroken cookie. We have to accept that we're delicious. We're good. We are loved by our Heavenly Father, broken or not. When you went out on your missions, and many of you have returned from missions, you were okay with the people you were teaching being broken. That was part of the job, helping them get unbroken, or at least more unbroken. And you loved them just the same, broken or not, okay? Use that same love on yourself and recognize that that's the way your Heavenly Father sees you, the way you saw your investigators when you were out on your mission. I just want to, before we start today's lecture, thank you for what you've done for me. As I've told you, I have gained more from this experience coming to BYU than my students have. I thought I was going to be doing you all a favor. It didn't turn out that way. You're doing me a favor. You have brought new life to me. So thank you. Would someone be willing to give us an opening prayer today, the last lecture of the semester? Thank you.
Our Father in heaven, we love thee so much. We're so grateful for the opportunity we have to study here at BYU and to be in this class with Dr. Francis. We're so grateful for him and for his amazing teaching abilities and love for all of us. And we're grateful for this Christmas season that we have to celebrate our Savior. And please bless that we can all seek the Spirit and feel the Spirit throughout this time. And we say this in the name of Jesus Christ. Amen.
Okay. Let's, for the first part of the lecture, I'm going to kind of recap what you learned in that last tutorial. And then I'm just going to go through a bunch of sample problems similar to what you would be expected to solve on the last midterm. So the big idea here is if you're faced with a picture like this and you're asked, where did the incident pulse come from? Now you remember there's always three pulses. There's the incident pulse, I sometimes call it the mother pulse, that comes into this boundary. There's the boundary right there between two springs. And when that mother pulse gets there to that boundary, it splits. It splits into what I call the twins. And one of them goes one way, one goes the other way. And the question is, which one is the reflected pulse? The reflected pulse is the one that goes back the way the mother came from. The transmitted pulse is the one that goes into the new medium, the new spring that keeps on going, okay? And so the question is always, which of those is the reflected and which is the transmitted pulse? And I have a feeling, a deep, abiding feeling that you're going to have a question like that on the exam. Now, suppose I had two springs and this one has a small mass density and this one has a big mass density. It's a fatty spring, okay? So the question is, which one's going to be the fast one and which one's going to be the slow one? Tell your neighbor real quick. Okay. I hope that everyone immediately said that the one on the right is the fast one and the one on the left is the slow one. And the question then begs itself, why? Why? And you remember that the speed of pulses for a transverse pulse on a string or a spring is given by that formula right there. And that tension force, is that going to be bigger in the red spring or the blue spring? Yeah, it's got to be the same. By what law? By what law? Shout it out. Third law. Yeah, that third law just keeps coming back and blessing our lives. And so that means if that's always the same, whichever one has the bigger mass density, whichever one is heavier, is going to have the smaller speed. Now you remember that we think of these as football linemen holding hands and passing the pulse down from one to another, and then a bunch of ballerinas here passing it down, okay? And it's just harder to get that pulse to go through a bunch of football players than it is a bunch of ballerinas. Now, let's look at these pulses. If we have a mother pulse come into that boundary, let's first of all talk about the transmitted pulse. Is the transmitted pulse going to be on the same side or the opposite side? Tell your neighbor. Okay, just for fun, let's vote with our clicker, get some attendance points.
Oh, yeah, this one. This actually doesn't matter. Because it's
They have repetition on it when things. So, hey, we're like.
Okay, people, there are 271 votes. I brought 270 cookies. Some of you have not eaten a cookie, okay? As you're leaving today, make it so, okay? Get rid of these cookies. Get rid of these cookies. Okay, let's see how you voted.
I stayed out there.
Good, good. Really? Who are these people? The watermelon people. Oh, it's you guys there. Yeah, okay. Okay, the right answer is the same. When is the transmitted pulse the same on the same side as the mother pulse? When does that happen? Every stinking time, no exceptions, every time. Every time. You can take that to the bank. That's always going to be the case, always the case. Okay, and what is that transmitted wave or pulse going to look like when it gets to the fast spring? Is it going to be narrower, the same, or wider? Let's again use our clicker.
I would think.
Yeah, I wasn't gonna put watermelon this time.
Faster, out of waves.
That's like
Change velocity because it's the same pulse as frequency can change because of the wavelength. Looking at your brain, I'm taking it. Okay, I'm on.
Okay, there's 3 more votes that need to come in. Get your vote in. Last call.
I might.
Okay, the answer is C. Wider. So why? Now, in tutorial, the approach that was taken was to take 2 little pulses. Later, we found out that one of the pulses represented the front of a big mother pulse, and the other one represented the back of a big mother pulse. And then you looked at what the spacing between those pulses did when it got to the boundary. But I'm going to take a different approach. I'm going to represent that mother pulse by a school bus. But this isn't just any school bus. This is a magic school bus. A school bus that can stretch, or compress as needed. And the school bus is going from a very slow dirt road that's very hard to travel on to a nice, beautiful paved road. And when the front of the bus gets to that pavement, it speeds up. But the back of the bus is still back in the slow dirt road. And so it's still going slow. And so that bus stretches. And by the time all of the bus gets to the pavement, it's much wider. Now you can imagine the bus going the other way, where the front of the bus hits the slow dirt and slows down, while the fast bus in back is still going, compressing the bus. See if your neighbor, if that speaks to their soul. Make sure it speaks to their soul.
Am I on that? I don't. Thanks, back together. Like it's faster out.
Okay,
Yeah, front part of the bus, part is still.
so if I'm going into a fast medium, my pulse will stretch, it will become wider. Now, folks, don't worry about the amplitude. The amplitude is very, very difficult to predict. That depends on a whole bunch of different factors. What I can say is that the reflected pulse will always have a smaller amplitude than the mother pulse, because they're both in the same spring, and some of the energy has gone over into the other medium, the other spring. But we're never going to ask you about the amplitude, the height of the pulse, only the width of the pulse, okay? Now let's consider the reflected pulse, the one that bounces back, okay? If I'm going from this slow medium to this fast medium, am I going to come back on the same side or the opposite side? Again, let's use our clicker.
Watermelon. The lights, the heavy.
Because it's gonna hit that. Okay. But then like, it's like when you hit it.
Same size, it's still free.
Someone just suggested that I should have asked if you were on the bus. Okay, that's all of us. Let's see how we voted. Okay, same side win. That is correct. It is the same side. But why? Why? Tell your neighbor, give a reason. Watermelon. Huh?
No, it's
As I told you. That's not good enough. Okay, if you remember the previous tutorial where we just had one spring and it was either coming up to a fixed end at a wall or a free end at a wall, you found that it bounced back differently. If it was a fixed end, it inverted. If it was a free end, it didn't. Well, in this case, I'm going from heavy to light, and it acts like a free end, so it doesn't invert. If I were coming the other way from the red to the blue, that would be light to heavy. That's going to act like a fixed end. Now, why don't we just pretend that we're Galileo, okay? Galileo's genius was pushing physical situations to their extremes, to the the furthest out he could go with his mind. And let's imagine that this spring on the right is very, very light fishing line or dental floss, if any of you use that. The only person I know that uses dental floss is my son, and he's a dentist. Okay? So this we think of as a heavy lead chain. Okay, and so if I have something going from a heavy lead chain to dental floss, that's like a preamp. That's like, ooh, you're hardly there. Okay. On the other hand, if I'm coming from dental floss to a heavy lead chain, that's like hitting a brick wall. That's like hitting a fixed end. Okay, in that case, it's going to invert. Okay, now let's look a little deeper at that reflected pulse. If this pulse comes in and bounces right there back, what's the reflected pulse going to look like? Is it going to be this one on top or this one on bottom? Tell your neighbor real quick.
Like, they're gonna be like,
They're reflective.
children on
You're right. That's the leading edge.
Okay,
Comes out.
the key to this question are these arrows right here. The mother pulse is coming in to the right. The reflected pulse bounces and goes back to the left. And what we know is that the leading edge, the edge that's leading the charge that's out in front, has to stay the leading edge. Okay, it will always stay the leading edge. And that's different than we have for solid objects like a baseball. A baseball, one side will be going in front as it comes into the wall. The other side will be going out in front when it leaves the wall. But a pulse doesn't bounce like a baseball. Instead, it gets to the boundary and turns around like a snake and comes back the other way. So whatever was out in front stays out in front as it goes back the other way. Now, I have a handout here, and while we're handing out these handouts, I need some people to come down here if they didn't get a cookie and get themselves a cookie.
but I'm gonna.
Need a cookie? I'll bring one.
Sorry.
That's so angry. Stay.
So much knowledge in this. Crazy.
Because I'm.
Yeah, I just want to be.
And now-
How are you doing?
That way. Loaves and fishes, loaves and fishes. Any leftovers?
I would say both.
Thank you.
Exactly. Scotland.
So, probably gotta act.
That's a big.
Would you let us? I got my black money. It's $9. No, that's excellent.
Who needs one?
Like city. Oh, that was. Now.
Who needs a handout? The whole row?
Thank you. I'm like, I didn't know.
We're having a written conversation.
Okay. As I said before, I have a strong feeling that you're going to have a problem like this on that last exam, where you are shown the twins, okay? And what you should be seeing is a reflected pulse and a transmitted pulse. The mother pulse, the incident pulse, has already come into the boundary and split in two. And these two twins that were both born at midnight at this hospital right there are racing away from the hospital. This one's racing to the right, this one's racing to the left. And the question is, which one of those is the reflected pulse and which one is the transmitted pulse? And that's just another way of asking, which side did mom come in from? Okay, which side did the incident pulse come in from? So first of all, let's ask this question. Which is the fast spring? Now, in the previous slides, I always had the slow spring drawn really, really fat. Okay, and you say, oh yeah, that's the slow one right there. Okay, but these, one's not thick and one's not thin. They're the same width and they're going to be the same width on your test. So how do I tell which is the fast spring? Talk to your neighbor.
Those are the same. But actually. The mass density is low. This acronym already.
Okay. The key is recognizing that these twins were both born at the same time, midnight, at that hospital right there. And this twin has gotten a long way from the hospital in exactly the same amount of time that this twin has barely gotten to the end of the block. Okay, we took this picture and this one got further away. So the one on the left is the fast one and one on the right is the slow one. Now, in this problem, you're told that one of the springs is made of brass and one is made of steel, and that the steel is the one with the bigger mass density. And so that means the slow one is going to be the steel spring. Now, folks, if I could just pause for a moment. How many times in your life are you going to be faced with this situation where you've got two springs, one fast and one slow, that are hooked together? That's going to be what's going to decide whether you get the job or don't get the job. How many times do you figure? Yeah, zero. So why are we worried about this? Well, it turns out that this is something that happens over and over in nature and in many different contexts. Anytime you have any wave phenomena going from one medium into another, when it gets to the boundary, if the wave speeds are different, you're going to have some splittage. Some of the energy is going to go into the new medium, some is going to bounce back. And the closer you can get those two wave speeds to the same, the more of that energy is going to go through. Now, some examples of that. If you have a wave on the water that's coming into a bay, and there's this very, very abrupt change in depths. In Guam, where I went to high school, Agana Bay was 30 feet deep. And then suddenly you had the Marianas Trench, the deepest part of the ocean. And right there where waves came, you could see the waves come in and some of the energy go back because of that discontinuity, we call it. Something closer to home would be your stereo system. If you don't have all of the components of your stereo system impedance matched, have you heard that term? Impedance matched? If everything doesn't have the same impedance, your signal's going to come, and when it gets to the boundary between the two parts of your system, you're going to split the signal, and some of it's going to go through to your speakers, and some of it's going to go back to mess with your electronics, okay? So it's important in that situation. Another example of that are these two, boy, these two binoculars. These binoculars were $10 at a yard sale, okay? And they're not quite worth that, okay? Yeah. These are Swarovskis, okay? Swarovskis typically cost over $1,000. The higher end models can cost between $3,000 and $4,000. And the question is, how can this, which is doing the same function, cost $10 when this costs over $1,000? And yet they sell these. When people go into the store and they look through these, they say, whoa, that's worth the extra money. And folks, it is. I paid it, okay? And the difference is the way they treat the glass. When the light comes from one medium, air, to another medium, glass, you have this split where some of the energy, the light, goes through and some reflects back. The name of the game with good optics is to get as much of the light through to your eyeball as possible. And they have all sorts of very sophisticated tricks to make, I think the transmission on these are something like 88%, and not so here, okay? So this is something that you will encounter many times during your life, and the answer is always the same. And so whether we're dealing with waves on a spring or waves on the water or light waves, we always get the same physics. So that's why we're teaching you in the simplest case with spring, okay? Now, thank you. So let me go back to drawing that fat so that we can remember that it's the slow one there. Now, the question is, which one is the reflected pulse? Now, some of you have figured out a shortcut. You're able to look at that picture and say, oh, I know which one it is, okay? And that's okay. I hope by the end of today, we all know the shortcut. But I'd like to present a long cut, okay? The long cut is that this is one of those problems, and you've seen many of them during the semester, where there's only two possible answers. The mother pulse either came in on the right or it came in on the left. You had that problem where you had Billy and Elaine with their buzzers, and you wanted to know which one had the higher frequency buzzer. Well, hey, it was either Billy or it was Elaine. Okay, it's just there's two possible answers. When you are dealt one of those problems, you reach into your pocket, you grab out a quarter, and you flip it. Okay? Heads, it's left, tails, it's right. In other words, you guess and check. Once you guess, you check. And when you check, if you find that you guessed wrong, you still know the right answer, right? There was only two possibilities, and it's not this one, it's the other one. So let's do the guess and check method. I'm going to guess that it comes in from the left. So I'm going to guess that it comes in like this or like this. And the question is, which of these seems more reasonable? Tell your neighbor, which one seems more reasonable?
No, this looks better. It's the.
Okay,
It's between the two.
again, the key is remembering which direction these pulses are traveling. If the mother pulse came in from the left and the transmitted kept on going, the leading edge would stay the leading edge. And so that means that it has to be that one there. That one can't be right. So let's get rid of it. Now, if that came in, that's going to give me, am I hitting a free end or a fixed end? Yeah, it's going to be like a fixed end. Okay. And so that means that this is going to, when it hits the boundary, it's going to invert, turn around and invert. And that's not what we saw in our picture that we were trying to figure out. So that can't be. So what if it came in like this? Okay, if it came in like that, when it hit that fixed end, it would invert and go off like that. Well, that's what I saw. That's perfect. That's perfect. What's wrong though? Yeah, if I look at the transmitted pulse now, what's the transmitted pulse going to look like if the mother pulse came in like that? Well, it's going to be on the same side. And that's not what we saw in our picture. Okay, so we have tried every possible combination of mother pulse coming in from the left, and over again, and it fails. I guessed wrong. So that means it must have come in the other way. Now, if that came in the other way, is that going to be hitting a free end or a fixed end? A free end, because it's going from the heavy to the light. And so it's going to bounce back on the same side. Again, the leading edge is going to stay the leading edge. And the transmitted pulse is just going to keep on going through. In truth, I should have drawn this a little bit wider, should I not? That should have been a little bit wider. Okay, so we figured out the right answer. Now, what's the shortcut? Well, the shortcut is that the transmitted pulse never inverts, never, ever, never. But the reflected pulse flips half the time. It inverts whenever you're hitting a fixed end, and it doesn't invert whenever you're hitting a free end. So if you look at your picture of the twins, if they're on the same side of the springs, either both on top or both on bottom, it came in on the heavy side and hit a free end. If, on the other hand, they're on opposite sides of the springs, one's on top and one's on the bottom, it came in on the light spring, the fast spring, like it hit a fixed end and inverted. Okay, see if your neighbor followed that. If not, slap them hard.
You take it.
That makes
Make like a few.
Don't.
Yeah, you're right. You know, I hate the sun.
Okay,
I can say.
are there questions on this material from that last tutorial? Because we're going a different direction now. That's correct. Because the mother pulse came in from the right, reflected means bounce back. And so this would be the reflected pulse, and this would be the transmitted. Transmitted means goes into the new.
That's it.
Okay. Thank you for asking that question. Okay. A big part of what we've done is based on this idea of superposition, which is just a fancy sciencey name for atom up, atom up. Now, folks, again, this might seem like, when am I ever going to need this? And I'm going to tell you right now, right at the beginning of Physics 106, and then in the middle of Physics 106, and then at the end of Physics 106, okay? You're going to be using this over and over and over again, just like F net equals MA, okay? So what does it mean? It means that when two pulses come through each other, that's what they do. They don't bounce off each other, they pass through each other. And while they are passing through each other, the spring or string, whatever's carrying the pulses, is the sum of the two pulses. Let's look at that. These things are moving towards each other, and then they meet. And as they overlap, what I see is that on the left, all I've got is the green pulse, and so I draw that. But right here, I have 1 unit up on the green and 1 unit up on the red. Well, that's 2. And then here, I have 1 unit up on the green and a half up on the red. Well, that's 1.5. And then over here, I just have the red. And so it goes to that. Now, remember, in real life, we never have pulses with kinks, with sharp points like that. So you would never get this shape in nature. But we use these kind of pulses in our homework and on the exam to make it easy to do the superposition. So if we could have those pointy pulses, this is what the spring or string would look like when the two pulses were overlapped like that. Now they go a little bit further. And now here, I've got 1 up on the red and 1 up on the green. Well, that's 2. Here I've got 1 up on the green and 0 on the red. That's 1. And that's what the pulse is going to look like on that spring or string. And then they go a little bit further. Now on the left, I've just got the red pulse. So I do that. Here I've got 1 up on the green and a half up on the red. That's 1.5 up. And then here I've got 1 up on the green and 0 on the red. That's 1. And then over here I just have the green pulse. And sure enough, that's what the spring or string would look like. And then they go passing through each other, strangers in the night. You don't even know that song. That was before you were born. Okay, questions on superposition. It's super. Super. Oh, no questions? Okay. Let's turn that piece of paper over, and what you see is an old exam question. And folks, I got to tell you, I came from 31 years where I could get fired for preaching to my classroom. And so this is how I did it without getting fired. I put test questions that dealt with the tabernacle organ. And then people would ask, well, who's got the tabernacle organ? Oh, that's Mormon. Okay, so let's look at this problem. The Tabernacle Pipe Organ at Temple Square in Salt Lake City has 11,623 pipes with which to make musical tones. These pipes vary in length from 2 centimeters to over 10 meters. One of these pipes is open at both ends and sounds a 245 hertz tones as its fundamental frequency. And we want to know what the length of this pipe is. Well, the key is knowing the fundamental frequency. If I know the fundamental frequency and I know what kind of pipe it is, I can find the fundamental wavelength. And if I know the fundamental wavelength, I can use my football equation to find the length of the pipe. Well, let's do that. Our first step is always drawing a picture. If that pipe is open at both ends, they both have to be antinodes. And between any two antinodes, I have to have a node. I can't just go straight from an antinode to an antinode. That's just wind. That's not sloshing, okay? So the picture is going to look like that. Okay? Now, if I know the frequency, I can find the wavelength by the wave equation. V is going to be equal to F times lambda. And that's true for every harmonic, the first harmonic, second harmonic, third harmonic, fourth harmonic. But if I'm using the frequency from the first harmonic, I have to use the wavelength from the first harmonic. If I'm using the frequency of the third harmonic, I have to use the wavelength of the third harmonic. Okay, so if I solve this for lambda 1, that's going to give me V over frequency 1. That's going to be, V is 343 meters per second. That'll be on the front of the exam. And then we're told that the frequency is 245 hertz. That's going to give me 1.4 meters. Is that the length of the pipe? No or heck no? Heck no. Because I've just got one football here. There's a half, there's a half. And how many footballs does it take to make a wavelength? 2, always 2. And so I've only got half a wavelength. So that means that this pipe is going to be 0.7 meters. Now, if that reasoning didn't speak to your soul, use your football equation. Number of footballs times lambda over 2 is equal to L. I've got one football times lambda, which is 1.4 meters over 2, and that's equal to the length of the pipe. And that gives me my length is 0.7 meters. Does that seem straightforward? Questions on that? Okay. Draw the fundamental frequency standing wave pattern in the pipe from part A. Well, we did that. We are way ahead of it. Okay. Now, here's where we get all musical. A flute with one end open and one end closed wants to play the same tone, and by that we mean the same note. Okay? So, how long should that flute be such that its fundamental frequency is also 245 hertz? Talk to your neighbor, figure that out. Okay. I hope that where your mind is going is that if it's the same frequency, it's the same wavelength. And if it's the same wavelength, it's the same size football. But now, because that tube is closed at one end, I'm going from a node to an antinode, and the fundamental, the longest wave that will fit, goes straight from the node to the antinode. I only have half a football. Well, if a whole football is 0.7 meters, a half football is going to be 0.35 meters. Now, again, if that reasoning did not speak to your soul, use the football equation. The number of footballs times lambda over 2 is equal to L of the pipe. Well, I only have a half football times lambda, we said was 1.4 meters still over 2, and that's going to equal the L of the pipe. And that's going to give me the L of the pipe is equal to 0.35 meters. How we doing? Good. Now, a base lute, or sometimes called a bass lute with fisher people, okay? A bass lute, one end open, one end closed, and much longer than a regular flute, wants to play two. The length of the bass lute, is 1.05 meters. Which harmonic must be played to make this same frequency note? Again, the same note means the same wavelength, means the same size football, okay? So if I draw that bass flute, and I start filling it with half footballs, each half football has to still be 0.35 meters. And then I go the next half football. And then the next one. And it turns out that 3 times 0.35 is 1.05 meters. And that's the total length of that bass flute. So, which harmonic do I have there? Shout it out. The third harmonic. We are playing F3. Now, why do we call it F3? Because if we are cramming 3 times as many footballs into the same space, well, that means the footballs have to be 3 times smaller than the fundamental football. And if the footballs get 3 times smaller, the frequency gets 3 times bigger. And we always want to use that formula that the third harmonic is 3 times the first harmonic. And the 27th harmonic is 27 times the first harmonic. That is a powerful equation that we always want to use. And so what we say is that we're skipping the second harmonic. And we're just going from the first to the third to the fifth to the seventh to the ninth. See if your neighbor's still on the bus.
A little bit lost.
Got my
Okay. You're going to have several problems on your exam like this. Sam, there's a question right behind you there. I'm also going to promise you that you'll have one of these mock cone problems. Okay, so let's look at this problem at the bottom of the page. You look directly overhead and see a plane exactly 1 kilometer above you, flying faster than the speed of sound. The plane travels on a level path over the level ground for another 1.75 kilometers before you hear the sonic boom. How fast in meters per second is the plane moving? Well, let's draw a picture. The plane is 1 kilometer above your head. And when it gets a distance of 1.75 kilometers, that mock cone reaches your ear. And remember, the key to figuring out how fast this plane is going is finding that mock cone angle. Technically, it's a half angle of the mock cone, but we call it the mock cone angle, theta. And we can find that with just a little trigonometry. We know that the tangent of that angle is equal to the opposite side, 1 kilometer, over the adjacent side, 1.75 kilometers. And that means that the angle is going to be the inverse tangent of 1 over 1.75. Sorry. And that, it turns out, is 30 degrees. And then we use this formula that the sine of theta is equal to 1 over the Mach number. I can rewrite that as the Mach number is equal to 1 over the sine of theta. Well, in this case, that's going to be 1 over the sine of 30 degrees. And the sine of 30 degrees is 1/2. And so that means the Mach number is 2. And so that tells me that the speed of the plane is twice the speed of sound, or 686 meters per second. I hope that is straightforward to you and that you'll be able to work that problem on the exam. Now, folks, before we go to the other sample questions, it occurs to me that I brought these wave machines over here, slicing up my hands in the process, and I haven't used them yet. So let's use them real quick while we've got time. What we've got here is a slow wave on the left and a fast wave on the right. And so first of all, let's just look at the transmitted wave when it reaches this boundary between the two. These are coupled together. I'm going to send the pulse in on top, and you see that it gets into the other one on top. If I send the pulse the other way, if I start on top, it ends up on top. But you'll notice that it got narrower and went slower. Well, now let's concentrate on the reflected pulse. If I send it from the slow side, it's going to be like hitting a free end. It's going from the heavy to the light. And so I expect my reflected pulse to come back on the same side of the machine. If it goes in on top, it comes back on top. And that's what we see. Okay. On the other hand, if I send it from the other way, it's like hitting a fixed end. And if it goes in on top, it's going to bounce back on the bottom. And that's what we see. Okay. See if your neighbor saw what we saw.
That's that. That's you on the bus.
I know. Hold on. Me neither.
I think it's more the fact that
Okay. The rest of the lecture, the slides that I've posted at Max, just have sample questions similar to what you'll see on the exam. And in each case, I've placed the answer in red. So if we don't get to all of these problems, you can work them after the fact and check that you get the same right answer because it's in the slide. Now, we started out this part of the class talking about simple harmonic motion. And I made a promise to you that any problem dealing with the energy in a simple harmonic motion would be in a horizontal spring, not in a vertical spring, because the horizontal spring is more simple. Sam, could you kill that light right above? No, no, leave it on. Yeah, I wanna, I know what I'm doing. Just seems like I don't. Okay. So this block is attached to the string, and this would be the happy point, its happy place where it would stay forever if we didn't move it away from there. We're told that the spring constant is 200 newtons for each meter. And we know that the amplitude is 0.3 meters. So if I bring this out to 0.3 meters, or back here to 0.3 meters. These are the turnaround points, back and forth, back and forth, back and forth. And what we want to know is how far or how fast will the block be going when it gets 0.1 meters away from equilibrium. And it doesn't matter whether it's on the left or the right, it's going to be the same speed either way. We're just looking for the speed, which is always a positive number. Okay. We also know that this is a 4 kilogram block. Well, we have three formulas. The general formula is that the total energy is equal to the kinetic energy in the motion of the block plus the potential energy in the stretch or compression of the spring. We also know, and this always applies. We also know that a turnaround, it's got to stop to turn around. And so this would be 0, and all the energy would be in this potential energy bucket. But now delta S is equal to A. So instead of delta S, which is a general compression or stretch, I'm going to put A. Now, in these problems, the first step is always finding that total energy by hook or by crook. And here, I know the K, and I know the A. And remember to square that, folks. I wish I had better news, but a lot of you are going to forget to square that and get the wrong answer. And know this, I will work the problem without that square, and that'll be one of the choices on the multiple choice, okay? So this is going to be 9 joules. So now, since this point here is not at equilibrium and not at the turnaround point, I'm going to need to use this general equation. And so I will say 9 joules is equal to 1/2 times 4 kilograms times V squared plus 1/2 times 200 newtons per meter times 0.1 meter squared. And when I solve that, what I will get is 2 meters per second. Okay. Questions on that problem? You'll have at least one like that. Back in the back.
Amplitude half of a wavelength.
Whoop, 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 whoop. Oh, old man coming. Yes. I'm sorry? Oh, there is no wavelength in this. This is just an oscillation back and forth. This is simple harmonic motion. An amplitude is the furthest it gets away from the equilibrium point. Okay,
So did I?
from its happy place. Okay, let's look at the next one. When a force of 20 newtons is applied to a spring, it elongates 20 centimeters. What is the period of a 4-kilogram mass suspended from this spring?
So,
Now, you remember, we had two methods of finding the spring constant. We had the static method where we just hang a mass on the string and see how much it gets stretched. And then we had the dynamic method where we bounce the mass on the spring and we measure the period and use that formula for period. Well, with the static method, we're using Hooke's law. The force by the spring is K delta S. If 20 newtons is going to stretch this by 20 centimeters is 0.2 meters, then K is going to be 100 newtons per meter. Now, what I would like is the period of a 4-kilogram mass on this thing. Well, the period is given by 2 pi times the square root of m over k. So that's going to be 2 pi times the square root of 4 over 100. Well, 2 pi is 6.28, and the square root of 4 is 2. The square root of 100 is 10. And so this is going to give me 13, 12 and a half divided by 10, or 1.28 seconds. Okay, and indeed, when we pull up the answer, it's about 1.3 seconds. Okay. A periodic wave on a string is observed to have exactly 2 cycles in a 3-meter section of the string. The crest moves at 20 meters per second. What is the frequency of the wave? This was an old exam question that crashed the class. The class just, whoa, and it was that word cycle. We didn't do anything with bicycles. This is not a mountain biking class. Cycle means repetition, means wave. Okay, so all this is saying is I've got 2 waves in a 3-meter section of the string. What's the wavelength? 1.5 meters. And if I know the speed and I know the wavelength, I can find the frequency with the wave equation. If this is 20 meters per second and this is 1.5 meters, lambda is going to be 13 hertz. And so the correct answer here is 13 hertz. Now, folks, there are several problems on this test that you're going to be taking where that's the answer. V equals frequency times lambda. Okay, that's it. Now, folks, we don't have time to work this problem. I will post the solution in all its gory detail as soon as I get back to my office. This problem is much more messy than you would be expected to do on your exam. Okay, so why don't you, everyone, come eat up these cookies, especially if you didn't get one at the beginning, but make them gone, people. Make them gone.
I don't want to.
Oh, my bad. Thank you.
I'll be here next semester.
Okay, I'll be here next semester.
Thank you.
Thank you. Oh, thank you. Oh.